All right, let's dive in. Today, we're going to take a quick user's tour of what is, without a doubt, the most complex object in the known universe. And yeah, I'm talking about that 3-pound marvel of engineering sitting right between your ears. I mean, think about that for a second. How does a lump of tissue, about 3 pounds worth, create your entire reality? Seriously, everything you see, everything you feel, every memory, every dream, it's all generated by this intricate biological machine. So the big question is, how does it actually work? Well, that's exactly what we're going to unpack right now. Okay, so here's our game plan. We're going to start with a high-level map of the brain. Then, we'll look at how this thing is powered. After that, we'll meet its most important citizen, the neuron. We'll figure out how it sends messages. And finally, we'll check out the amazing tech that lets us see all of this in action. All right, first up, the map. The easiest way to think about the brain is like a huge, bustling corporation. It's got all these different departments, and each one has a really specialized job. We call these departments lobes. And our first stop, well, it's the executive suite. So say hello to the frontal lobe. This is your brain's CEO, the big boss. This is where all the high-level strategic thinking happens. Planning your day, trying to decide between two options, or that little voice that stops you from saying something you know you'll regret later. Yeah, that's all coming from the corner office, the frontal lobe. Okay, from the CEO's office, we're heading down to the corporate library. This area is run by the temporal lobe. This is your head librarian. It's in charge of processing what you hear, making sense of language, and, this is a big one, filing away all your memories so you can find them later. I mean, without this librarian, learning anything would be pretty much impossible. Of course, it's not just a CEO and a librarian. You've got other key players in this system, too. There's the cerebellum. Think of it as the master movement coordinator, making sure you can walk without stumbling. You've got the pons, which is kind of like the central relay station or switchboard for all the messages flying around. And then there's the spinal cord, which is basically the super-fast information superhighway connecting the brain's headquarters to, well, the rest of the body. Okay, so a corporation this busy needs a ton of power, right? And the brain is no exception. Get this. Even though it's only about 2% of your body weight, it's an absolute energy hog. It uses a whopping 20% of your body's oxygen and calories. So it absolutely has to have dedicated fuel lines to keep running. Let's take a look at how this machine stays powered up. And when I say dedicated, I am not kidding. The brain demands a constant, non-stop flow of oxygen-rich blood. We're talking 24 hours a day, 7 days a week. There are no coffee breaks, no shutting down for the night. Any interruption, even for a few seconds, can be absolutely catastrophic. So how does it get this constant supply? Well, the whole delivery network is basically split into two major plumbing systems. You've got the internal carotid system, which feeds the front and middle parts of the brain. Think key arteries like the MCA and ACA. And then you have the vertebro-basilar system, which takes care of the back and lower regions, with arteries like the PCA. It's a really elegant two-part solution. Now, this is a super important distinction to make. The blood itself doesn't carry the information. It's not sending the emails, so to speak. It's just carrying the fuel, the oxygen and the glucose. The actual messages, that's handled by a completely different system, run by the brain's real star players. And that brings us from the big picture, the macro-level stuff, down to the micro. So let's zoom way in, past the lobes, past the arteries, and meet the single most important cell in this entire operation, the neuron. So what is a neuron? Well, it's basically a biological wire and a tiny transmitter, all rolled into one. Its whole job, its entire purpose in life, is to conduct these little electrical signals called action potentials. And here's the mind-blowing part. You have around 86 billion of them. Billion. And together, they form this unbelievably intricate communication network that creates, well, everything. Every thought, every feeling, every single memory you've ever had. Okay, so if the brain is this giant network of billions of neurons, how in the world do they talk to each other? It's not as simple as just zapping electricity around. It's actually this brilliant combination of both electrical and chemical signals. Think of it like a microscopic postal service that runs at the speed of light. So here's how the basic handoff works, in 3 steps. First, an electrical signal, that little zap, travels all the way down the length of one neuron. Step 2, when it gets to the very end, it triggers the release of these tiny chemical messengers called neurotransmitters. Then, step 3, Those chemicals shoot across a microscopic gap and are picked up by the next neuron in line. And if the message is strong enough, that neuron fires off its own electrical signal. It's like this incredible, super fast relay race. And this really gets at a super important idea. You see, even though all these brain cells are packed in there super tightly, information doesn't just, seep from one cell to the next. It's all about the specific connections. It's all about the wiring. The real power of the brain isn't just the cells themselves, it's the incredibly complex and specific way they're all wired together. For most of human history, all of this was just a complete black box. Scientists knew that it was happening, but they had no way of seeing how. But now, thanks to some absolutely incredible technology, we can actually watch the brain at work. We can literally see thought happening in real time. So, one of the most powerful tools we have for this is called fMRI, and it works by tracking blood flow. Remember how we said active brain areas need more fuel? Well, it's simple. When a part of your brain gets busy, it calls out for more oxygenated blood. And here's the brilliant part. fMRI can detect the tiny magnetic difference between blood that's carrying a lot of oxygen and blood that isn't. This change is what we call the bold signal. And we actually have a few different ways to peek inside the working brain. An fMRI, which we just talked about, measures blood oxygen. A PET scan is a bit different. It measures metabolic activity using a radioactive tracer. Here's a good way to think about it. fMRI is like looking at a city at night and seeing which buildings have their lights on. PET scans are more like tracking the fuel delivery trucks to see which buildings are using the most power. Both give us an amazing map of brain activity, just from slightly different angles. Now, these imaging technologies are amazing, but they're just one part of a much bigger scientific toolkit. Our modern map of the brain has been built, piece by painstaking piece, by combining everything: fMRI studies, PET scans, studying patients with specific brain injuries, even electrical stimulation during surgery. It's this massive scientific puzzle, and we're still putting the pieces together every single day. So when you put it all together, we are literally building an increasingly detailed user's guide to our own minds. And that leaves us with a really profound question, doesn't it? Now that we can actually map the brain, now that we're starting to understand the blueprint of our own consciousness, what's the next chapter? What will we do? And maybe more importantly, what should we do with that map?